I'm Bart Smith. I do experimental fluid mechanics, and my lab, the Experimental Fluid Dynamics Lab at USU, is focused almost primarily on validation experiments applied to nuclear power generation. So we do measurements of flows that we think are relevant to nuclear reactors, so that they can be compared to computer models to make the computer models better.
Inside we have a bunch of cylinders, or an array of cylinders, which model the fuel rods within the nuclear plant. And so with this, we can measure the flow as the flow goes past these cylinders, which is very crucial in the heat transfer in a nuclear reactor.
About 3 years ago, I received a grant from the Nuclear Energy University program to build a new facility specifically for heated flows to do validation, to collect validation on, and that's our transient mixed convection wind tunnel, which is out in the technology building.
So this is our mixed convection wind tunnel. You can see on the right side back there, the shiny side is our heated plate. The heated plate will either assist or go against the forced flow from the blower. So right next to the plate, hot air rises, and the blower can either go in the same direction or against it. That's why the whole thing will rotate. So a lot of reactors, I guess people are scared of them melting down. The reactor can cool itself without any flow. That would help reactors, I guess, more acceptable. So we can use the results from this to help validate the reactor cause for those self-cooling reactors. And so if the flow, like the fan, stops blowing, it's still going to cool itself.
It's a totally unique facility. I'm pretty confident there's nothing like it in the world. The manufacturer of it had proposed one similar to somebody, but it was never commissioned. So it was his idea to make the large Ferris wheel type arrangement that allows us to invert it. All of these tests have two major parts. One is the facility, or the geometry that we're putting fluid through, and the other is the measurement techniques that we use. And so, the measurement techniques are pretty fixed. We use something called particle image velocimetry, which is a laser-based technique where we can take pictures of tiny particles in the flow that don't have any bad effect on the flow. They don't change it. We track where those are going to determine the velocity field inside the apparatus. That way we can measure things without putting probes in there that might change the way the flow goes.
So most of our measurements that we take are required using particle image velocimetry, or PIV. And PIV is a measurement technique that we seed a particular flow with particles that, such as olive oil droplets or whatever, and we will illuminate those with a laser, shown here in a laser plane or a sheet. And that sheet is then, images of that sheet are taken using this camera in two different images at very small increments of time, or microseconds apart. And from that we can calculate, see the distance, the travel of the particles, and calculate the distance or the velocity of the particles.
Well, we believe that this work will improve computer models that are used to both design and investigate the safety of current plants or new ones. So at the end of the day, what this should allow is for us to ensure that our current plants are safe, that we're running them to their full capacity, and allow us to build new plants.